This is slide 32 of the chapter 18 PowerPoints. What we need to talk about now really is it's the juxtaglomerular complex. So we have to go back to where the afferent arteriole and the efferent arteriole kind of enter and exit the glomerulus here at this point. So what you also have going on here, if we go back to, in fact, let me blow this up. Okay, so if I blow this picture up so you can see the nephron a little better. All right, you see how this is your renal corpuscle, and then you go into the PCT, and then the descending limb, ascending limb of the nephron loop, and now you're going into the DCT, and there's a portion of the loop that goes up through the in between the afferent and efferent arterioles, and that portion of the nephron loop is part of the distal convoluted tubule, or the DCT. So here we can see it blown up. So these are the cells of the DCT that contact the cells that line the outside here of the afferent and efferent arterioles. So all of these different cells have like sensors. They're sensory receptors. So we've got, notice the macula densa are cells of the DCT that are in contact with the arterioles. And then what else do we have? The juxtaglomerular cells. The juxtaglomerular cells are in this region here. And so now let's go back to the notes so you can know what I'm talking about. The juxtaglomerular complex consists of the cells of the macula densa, which is here. That's the region of clustered cells in the DCT closest to the glomerulus. So there's these cells right here. They're cuboidal epithelial cells, simple cuboidal. Then the juxtaglomerular cells are the unusual smooth muscle fibers in the wall of the afferent arteriole. So they're here and here. So we have macula densa, juxtaglomerular cells, and these make up the juxtaglomerular complex. So the function of this complex is to regulate blood volume and blood pressure through the secretion of erythropoietin, or EPO, and renin. Remember, EPO stimulates the production of more red blood cells. It stimulates erythropoiesis, or the production of more red blood cells. So it's going to, when the kidneys secrete EPO, that's going to cause the blood volume to raise and blood pressure to raise, because you're adding red blood cells to the blood. Renin is going to cause the blood volume and blood pressure to raise as well, but by raising the blood volume through water, through the reabsorption of water. Okay, so this table 18-1, lists the different components of the nephron and collecting system and gives you the primary function of each one. This is a really good table, table 18-1, and let's see which slide it is. I can't see it unless okay, it's slide 34. Slide 34, table 18-1. Okay, the renal corpuscle, the primary function is filtration. The PCT, the primary function is reabsorption. The nephron loop, the descending limb is reabsorption of water. The ascending limb is reabsorption of ions. In the end, the nephron loop's function overall is to concentrate the urine, to produce concentrated urine. Okay? The DCT, the function is reabsorption and secretion. The collecting duct, reabsorption of water, reabsorption or secretion of sodium, potassium, bicarbonate, and hydrogen ions. And all of this is selective. By the time it gets to the collecting duct, it's just to kind of fine-tune what's going to end up staying in the blood and leaving with the urine. The papillary duct just conducts urine to the minor calyx. So by the time the filtrate has reached, the tubular fluid has reached the papillary duct, it's now urine. Checkpoint question. damage to which part of the nephron would interfere with the hormonal control of blood pressure? Well, it would be the juxtaglomerular complex. So damage to the DCT and the juxtaglomerular complex region is where the DCT connects with the afferent and efferent arterioles. Okay, the metabolic waste in urine consists of primarily urea, which is the most abundant of the organic waste, formed during the breakdown of amino acids, creatinine, which is generated in skeletal muscle tissue from the breakdown of creatine phosphate. Skeletal muscle breaks down creatine phosphate to help produce ATP. And then uric acid is formed from the breakdown and recycling of RNA, which is one of our nucleic acids. So this is a list of the normal laboratory values for solutes in the urine and the blood plasma. Just some interesting things to point out. I mean, sodium varies in the urine and the plasma. Potassium tends to be very low in the blood plasma compared to in the urine. And chloride ions can vary. Bicarbonate, very low in the urine, but higher in the plasma. But as far as glucose, this is where it's interesting to me. The urine is going to contain almost 0 milligrams per deciliter of glucose. So almost no glucose, almost no fats, 0 proteins. And if you see any of that in the urine, that is a sign that there's something wrong. Glucose in the urine is going to be a sign of diabetes. It's a sign that you had too much glucose in your blood in the first place, and it couldn't all be reabsorbed from the filtrate back into the urine. There weren't enough glucose carriers. So you had too much glucose in your blood, basically, if you end up having any in your urine. And proteins in the urine is probably going to indicate some kind of kidney damage. So you really want to see for the nutrients, for metabolites and nutrients, you want to see very little in the urine and a lot more in the plasma because you want to see that those nutrients are being reabsorbed. And these are normal laboratory values for the nitrogenous waste. Of course, it's really, really high for urea and definitely higher for all of these wastes, urea, creatinine, uric acid, ammonia, than what you would find in the plasma because they are waste and they would be toxic if they built up in the plasma. But the main thing I would just say is to know that your nutrients, glucose, lipids, amino acids, and proteins, especially glucose, lipids, and proteins, you expect those values to be 0 in the urine. All right, so where does the filtration pressure come from? It comes primarily from, it's a combination of pressures that contributes to it, but the primary force that contributes to the filtration pressure is blood pressure. So if there's a serious loss of systemic blood pressure, then that can result in the loss of filtration and a fatal reduction in kidney function. So kidney function and our cardiovascular system and our blood pressure are all interrelated. If one goes, the other goes, in either way. It can be if the kidneys go, that will cause the cardiovascular system to go. If the cardiovascular system goes, that will cause the kidneys to go. They're interdependent on each other. So we measure filtration by GFR, or glomerular filtration rate. This is the amount of filtrate produced in the kidneys per minute. So the average GFR is 125 milliliters per minute, or 180 liters per day. Our kidneys, on average, filter 180 liters of blood per day. That's a very large number if you think about it. I always think about liters in terms of a 2-liter drink. So that is 90 2-liter drinks, 90 of those. That's how much blood your kidneys filter per day. So over 99% of the filtrate that over 99% of that 180 liters per day is reabsorbed back into our blood once it reaches the renal tubules. So a summary of the events at the PCT: 60 to 70% of the filtrate volume is reabsorbed at the PCT. This is 100% of the glucose, amino acids, and other organic nutrients are reabsorbed. All of the important stuff that needs to get to our cells are reabsorbed. Then there is the active reabsorption of ions like sodium, potassium, calcium, magnesium, bicarbonate, phosphate, sulfate. Some of this is hormonally regulated. For example, parathyroid hormone regulates calcium reabsorption. And then there is some active secretion in the PCT as well. And remember, reabsorption means back into the blood, but some active secretion of hydrogen ions, for example. Hydrogen ions can be secreted from the blood into the filtrate to regulate pH. When you add hydrogen ions to a fluid, you lower the pH. When you remove hydrogen ions, you raise the pH. So if you were to secrete hydrogen ions into the urine, you would be raising the pH of the blood. Okay, now the summary of the events at the nephron loop. The filtrate entering the loop already has water and many solutes removed. So the nephron loop removes more than half of the remaining water and about 66% of the remaining sodium and chloride ions. The descending loop, remember, is permeable only to water. So as the filtrate moves down the descending loop, it becomes more concentrated because it's losing water. The ascending loop is impermeable to water, but it pumps sodium and potassium ions out. So as you move up the ascending loop, the fluid gets more dilute. And what this does, and this is something that takes a lot of explaining and a lot of studying to understand, but this process creates the concentration gradient in the medulla. It concentrates the urine. It's the best way to say it, easiest way to learn it, even if you don't really quite get it. That's what this process does, is it concentrates the urine to a level that it needs to be. It results in highly concentrated waste products at the end of the loop. The events at the DCT, this is where final adjustments are made in the fluid composition and concentration by active secretion. So one example is the active transport of sodium out of the tubular fluid and into the blood. And this can be exchanged for potassium or hydrogen ions. This is increased in the presence of aldosterone. So the overall effect is that the sodium in the blood increases and the potassium decreases. And it will counteract low blood sodium or high blood potassium levels. So aldosterone will help to increase sodium levels in the blood and decrease potassium levels. And so these are things that are regulated types of things. You know, it all depends on the levels that the levels of sodium, potassium, hydrogen that are in your blood and in your urine in the first place. And these final adjustments are made to control those levels. So this is how your kidneys help regulate the concentration of solutes in your blood plasma, in your blood that's dissolved in your blood. And also water. You know, because if aldosterone causes you to the sodium in your blood to increase, it's also water's going to follow. So it's also going to increase the volume of water in your blood. It's going to increase the overall volume of your blood, which will increase your blood pressure. So these are all adjustments that are made to fine-tune the concentration of your blood and also the blood pressure itself. All right, water reabsorption and ADH. ADH is antidiuretic hormone. Antidiuretic hormone. And a diuretic is something that causes you to your volume of urine to be large, for you to urinate a lot, whereas antidiuretic will cause you to retain water. So, in the absence of ADH, the DCT and collecting duct are impermeable to water. Water stays in the tubule and is excreted. So the result is a large volume of dilute urine. But in the presence of ADH, the DCT and the collecting duct are now permeable to water, so more water is reabsorbed, and that concentrates the urine, and that causes you to release a smaller volume of concentrated urine. So when ADH is secreted, and in the presence of ADH, you don't urinate as much, and your urine is going to be more concentrated. When you are dehydrated, this promotes the production of ADH. And this is a picture that shows you the effects of ADH. Basically, what you can see here is in the absence of ADH, you have a large volume of dilute urine because the water is staying in the DCT and the collecting ducts, whereas in the presence of ADH, now you see water leaving the DCT and the collecting ducts. So your urine is going to be concentrated and there's a small volume of it. Now we'll summarize kidney function, just a summary of it. Here at the renal corpuscle, we have filtration, that's step 1. And then as the filtrate moves through the PCT, step 2, in the PCT, you have mostly what's going on is the reabsorption of the important stuff like the glucose and amino acids reabsorbed back into the blood. And then you have the descending limb of the nephron loop, where you have water is leaving and the urine filtrate is becoming more concentrated to the bottom of the loop. And then as it moves up the ascending limb, the opposite happens. No water can leave, but solutes are able to be pumped out. So you end up with a less concentrated volume at the top of the loop. It's very concentrated at the bottom of the loop, less concentrated at the top. Then it moves to the DCT, where mostly there's like adjustments being made, some secretion from the blood back into the urine. Particularly this involves water, potassium, and sodium ions.